Hey everyone, and welcome to this explainer. Today, we are jumping straight into some truly foundational concepts. We're going deep into the meticulous and honestly highly structured world of dataset engineering. We're pulling all of this directly from Chapter 8 of Chip Huon's amazing book, AI Engineering: Building Applications with Foundational Models. So, if you've ever found yourself wondering what actually goes on behind the scenes to make generative AI so incredibly powerful, well, you're in exactly the right place. We're going to demystify all that unseen, gritty work that transforms raw information into highly intelligent models.
Okay, so here is our roadmap for today. We'll be covering number 1, the data-centric AI shift. 2, the art of data curation. 3, acquisition and annotation. 4, synthesizing new AI data. 5, distilling models for efficiency. And finally, 6, processing and cleaning data. Let's just dive right in.
Section 1. The data-centric AI shift. You know, in the early days of AI, the focus was heavily on a model-centric approach. Researchers were just trying to build better, massive architectures on top of completely static data. But today? Well, heavily championed by Andrew Ng's 2021 competition, we've made a massive pivot to a data-centric approach. So instead of endlessly tweaking the model, the goal now is to relentlessly improve the data itself. We're talking fixing incorrect labels, hunting down edge cases, and augmenting inputs. And the crazy thing? It gets significantly better results while using way fewer resources. It's a total win-win. Now, dataset engineering is essentially all about curating, generating, and annotating data for your models. But there is a huge difference in how we apply this today compared to the past. Traditional machine learning, it was close-ended. Think of a standard spam filter, right? An email is either spam or not spam. Pretty simple. But foundation models are open-ended and completely unstructured. Annotating an open-ended generative text query is just vastly more complex than labeling a spam email. It totally flips the engineering challenge on its head.
Moving right along to Section 2, the art of data curation.
If you think of model training as cooking, the data fed into the model is the ingredients. I absolutely love this comparison from the text. So data quality? That's the freshness of the ingredients. I mean, you can't make a 5-star meal with spoiled food, right? Data coverage is having the right mix, making sure you don't accidentally dump way too much salt or sugar into the recipe. And data quantity is simply having enough ingredients to actually feed everyone at the table.
To keep those ingredients fresh, your data actually needs to hit 6 key dimensions. It's got to be relevant, aligned with the task, consistent, perfectly formatted, unique, and of course, compliant. And to prove just how crucial this is, look at the creators of the Yi model family. They found that just 10,000 carefully crafted, high-quality instructions easily outperformed literally hundreds of thousands of noisy, low-quality ones. Quality trumps sheer volume every single time.
When you actually chart out fine-tuning performance, it's fascinating. You see distinct performance curves based on the number of tasks for 8 billion, 62 billion, and even 540 billion parameter models. As you add more fine-tuning tasks, the performance climbs. But here's the catch. Quantity is heavily bound by budget. Let's say you only have 10 grand for data annotation, and human examples cost $2 a pop. Well, you're maxing out at 5,000 examples. It's this constant tug of war, balancing your budget between spending on data versus spending on compute.
All right, Section 3, acquisition and annotation. How do we actually get this data? Well, the primary methods involve sourcing public sets, outright purchasing proprietary data, paying humans to manually annotate, and synthesizing brand new data. The ultimate goal here is to produce a sufficiently large data set that has the exact quality and diversity you need. And, absolutely crucial here, this all has to happen while strictly ensuring user privacy and regulatory compliance.
But wait a second. That brings up a massive, very real hurdle in AI engineering. What on earth do we do when real data is completely off limits? How are we supposed to train models for fields like healthcare or insurance, where real patient records and sensitive financial claims are, rightfully so, locked down by privacy legislation?
Which brings us perfectly to Section 4, synthesizing new AI data.
So we basically have 3 primary synthesis options. First is rule-based generation. This is your classic procedural generation, the kind used in gaming to create endless levels or maps. Then we have simulation. This is incredibly cool for things like sim-to-real robotics, where algorithms practice in physics engines with zero physical risk, or even climate scientists simulating extreme weather patterns. And finally, we've got AI-powered synthesis.
This is where we use advanced AI to simulate complex things, like the outcomes of arbitrary program APIs, without ever actually executing them. But hold on, we have to be really careful here. Relying heavily on AI to generate your data comes with some pretty unique risks. The biggest one? Obscured data lineage. Look, if the AI you used to synthesize your data was trained on copyrighted material, or even worse, was trained on the exact evaluation benchmarks you plan to use, well, your new model is now quietly contaminated. Without clear lineage, it becomes almost impossible to trust your model's commercial viability.
Next up, Section 5, Distilling Models for Efficiency.
This leads us right to model distillation. Basically, this is a method where a smaller student model is trained to mimic a much larger, way more expensive teacher model. And how do we do that? By using data that was entirely generated by the teacher. It is a brilliant way to create a significantly cheaper and faster model that still manages to retain performance comparable to that massive original model. Honestly, it's a total game changer for deploying applications at scale.
And finally, Section 6, Processing and Cleaning Data.
Back to our kitchen analogy, the first big enemy on the chopping board is duplication, and it shows up in a bunch of different ways. You've got whole document duplications, intra-document duplications, like a single paragraph just repeating itself inside the same file, and cross-document duplications, where maybe a popular quote shows up in thousands of different articles. Duplicate data doesn't just waste your compute time, it actually harms performance. The author notes that duplications have been shown to degrade an 800 million parameter model all the way down to the capability of a 400 million parameter model. I mean, that is a massive, totally preventable loss in efficiency.
So how do we fix it? You can systematically apply a few different steps. You usually start with pairwise comparison, which looks for exact or fuzzy matches. From there, you can move to hashing techniques, things like min-hash or Bloom filters, to bucket similar examples together. And then, for those really sneaky hidden duplicates, you bring in advanced dimensionality reduction and vector searches. Your data also desperately needs to be filtered of noise. Get this. Databricks discovered that simply stripping out extraneous HTML and Markdown tags from their scraped internet data improved their model's accuracy by a massive 20%. At the same time, it reduced their input token lengths by 60%. I mean, that is a staggering return on investment just for formatting your data correctly. But I do want to ground us with a pretty stark reality straight from the author. Despite all these fancy algorithms and vector searches we just talked about, dataset engineering is gritty, unglamorous work. It is mostly, as they put it, toil, tears, and sweat. It's full of frustrating, hair-pulling moments, like, discovering your entire model is malfunctioning just because a single column of float variables was accidentally stored as integers and rounded off. Yep, that actually happens. So I'll leave you with this final thought to ponder. We are quickly entering a world where powerful foundation models are becoming highly accessible, open commodities. If everyone has access to the exact same kitchen and the exact same appliances, the winner is going to be the one with the absolute best, most meticulously curated ingredients. Thanks for joining me for this explainer on dataset engineering. Now go out there and start curating.